I'm currently a lead researcher at Hugging Face, where I'm working on multi-modal models. And before this, I was working in meta AI research, where I used to work on vision and language problems, but also was helping on the production side of the things with products like marketplace, search, and others. So it was all over the place. So today we are going to talk about foundation models for vision and language alignment. So in the past few months or like even the years, like there are a lot of foundation models that are popping up around generative AI. Specifically, you must have seen like ChatGPT and like DALL-E 2 before that. In this particular talk, we are going to talk about specifically the vision and language alignment, like how do we align the two modalities that exist separately generally. So the agenda today is to like first learn how to like build a unified foundation model, which is a unit paper from ICCV 2021. And then we will learn how to take it step further by pre-training it. And then finally, we will talk about some nuances of the evaluation when we evaluate these models and how to like step up these evaluation to the next step once we build these strong vision and language aligned models. So the question is like, how do we build foundation models that can solve tasks across modalities? By modalities, I mean here specifically NLP, natural language processing, computer vision, and also like the domains which require the combination of both of them in order to do anything on top. An example would be visual question answering, where you're answering something on an image, a question on an image, and then you require to like leverage both the text domain as well as the computer vision domain to like answer both of them. So domain specific tasks come with a variety of challenges, but first we will answer like, why do we even need to care about this particular aspect of the field? So the first part is that architecture and the learning objectives are two domain specific. Like if you think about vision, like for the past few years before the transformers for the visions were introduced, they were very specific to the vision itself and didn't really work with text. And similarly for the text before transformers were introduced, we only had LSTMs, which didn't used to work for vision. So the architecture as well as the learning objectives today, for example, language modeling objective or the other objectives such as diffusion objectives really work well for vision or either NLP, but they don't work cross-domain. So the other part of this is why do we want a unified model is that like for n tasks, you need to serve n models. If you don't have a single model, this is not resource friendly and actually consumes a lot of compute and is expensive. Then there is no sharing of knowledge or resources. Like BERT shares its common domain across all of the NLP tasks. And then like, for example, FastRCNN shares its base for like object VBox classification or object or the bounding box regression. But there is no sharing of knowledge across domains. For example, let's say I learn something from vision. How do I apply that knowledge to NLP as well? So there is no sharing of knowledge or resources cross domain generally. Then the shared trunk and the multitask currently, like we discussed, is only working in a specific domain. For example, ChatGPT only works currently for just for the text, but doesn't really incorporate images in any way. Like, how do we move one step further from it? So that now we discuss like, why do we need to do this? What are the challenges we face when we start doing it? So the first problem is that once you start moving beyond one single domain, let's say in this picture, like I'm showing you like various tasks that are across domains, like object detection is a purely vision task. Then VQA and SNLIV require using both of the domains to answer or like correctly predict these questions. Then MNI, QNLI, and QQP are all of the glue benchmark tasks, which are NLP tasks and only involve text. So if you want a model that works across all of these tasks, you need to like do some sort of multitasking. But in general, whenever you go to do like multitasking, it requires very careful control and experimentation. So you can't like learn one of them and then lose the other information. So like when you like try to move from unimodal domain, which are NLP and CV, to multimodal domain, you usually lose information. So there is a forgetting that happens. You either do good at the combination of the task, but you start doing worse on the unimodal task. So this is not something that we want. Also, like the architectures are very domain specific, as we discussed. Like we have VIT, we have like transformers for text, but like we can't really directly combine them. So let's take a little bit detour to like the history of the transformers. So as you might know, like in the NLP domain, BERT has been like the starting foundation model, which basically was able to like use a shared trunk to solve many tasks. And then like in image side of the things, like vision transformers came in, and then the transformers also overtook the vision domain. And then similarly in the combined form, where like actually you have NLP as well as the vision, you can like use visual BERT, which is also transformer alternative. And then you basically like feed the images and text to this visual BERT, and then it can do variety of tasks on multi-modal reasoning, such as VQA and others we will see soon. So like transformers as of now are like all of the domains, including audio as well. So they have been like quite successful in like at least unifying the architectures. Then like the question that comes on the mind is like, can we actually help use transformers to like handle multiple domains in a single model? So in this particular work, like we try to do this by learning a single transform model, which we call unit, which is basically short for unified transformer. So like in this figure, we want to address vision only tasks such as detection, multimodal reasoning tasks, and VQA, and like blue benchmark tasks, all within a single shared model. So how do we do this? So we extend the transformer encoder decoder architecture, which you might have seen in the translation applications, by allowing it to take either image input or text input or even both, and handle tasks across domains. So this includes vision only tasks like detection. So you can see there are two encoders here. So we basically build two separate encoders for image and text inputs. And if both of them are present, we concatenate after the individual encoders and then pass them to decoder itself. So the question is like, once you have this unified representation, how does the decoder know like which task you are doing? So what you will do is like, you will have a set of query embedding vectors for multiple tasks that can produce not only stuff like bounding boxes for object detection, but also other outputs like VQA. This query embedding vectors also tell the model like which particular task is trying to do. So this is how it works. And we call this model like unit. And we hope that by training this model end-to-end on multiple tasks, we will be able to handle all tasks within one single model. So when we train this model jointly on all of the tasks that we care about, whether it's object detection or whether it's like any other sort of NLP task or the VQA task. So, but in practice, does it work? So yes, it does work. Like you have to like do a little bit more control on the exact sampling ratio of the task. You can feed different input and get different sort of query embeddings for like different things. It does work out of the box. So we can get it to converge on all of the 7 tasks, ranging from the ones that we discussed, and they can be addressed to a single encoder decoder architecture. So like in general, like if you are doing only the image only task, you can just pass in the image, not concatenated with anything. Then for text, you only pass in a text. If they are both, you just pass them both together and then pass it to a decoder. And then finally you collect its output. So these are some of the examples from object detection, question equivalence, and VQA, like where it actually works on all of the domains. So this like actually gives us a unified model, a foundation model to like move forward, like where we actually directly did the supervised training on all of the tasks. And now how do we move further from this? So the question is like, can we take it one step further? But the question is why do you want to do it? Because you basically don't leave the model without pre-training. So the model that we just talked about was just supervised trained on all of the tasks that we cared about. So if you don't do any pre-training, you are leaving a lot on the table. So there are some of the examples from the past, like when you actually do BERT pre-training, you get awesome results on the NLP task. Then you can do ME style pre-training on the vision transformers, and then you can see that also got impressive task on all of the downstream vision tasks. And then you can also do something like visual BERT or will BERT, where you actually pre-train on an image captioning data set, and then you can just get impressive performance on the vision and language task as well. So we talked about like that the jointly learning across domains is hard. Like the best for that we have unit, but like another problem that we face as workers, researchers working on the open domain problems, that the cross-modal pair data is not generally abundantly available. So CLIP was trained on 400 million examples, image caption examples, but the data was never released. So we don't have access to it. So all of the data sets like used in the prior work, for example, Google uses JFT 1.8 billion dataset, which is their internal dataset. They are not available openly and are proprietary. So for pre-training, we collected a data set from all of the publicly available sources, which was around 70 million image text pairs. And this collects basically everything that's publicly available. So after we collected this data set, Lion data set also came out, which is around 400 million in a smaller subset, but also like 5 billion in a larger subset. So you can also look at it. The PMD is just a little bit more cleaner than Lion in general sense. So you can pre-train on Lion, then fine-tune on PMD and so as such. So the other key challenge after this is that jointly, like before, jointly training was hard, but also jointly pre-training across domains is super hard, like in general, very super hard. Like objectives don't align with each other and are very domain specific. Like language modeling is very domain specific task, like image masking is super domain specific. Then also caption masking or like image text matching is also domain specific. Also, these models are like huge and they require massive compute. And as you move towards multiple data sets, you require even more compute. And then many vision and language data sets are not open source. So the next model that we want to talk about is FLAVA, which is Foundation Language and Vision Alignment Model. So this particular model is one foundation model that works across CV, NLP, and VNL, which is vision and language. And it has impressive performance. So in the paper, we test 35 tasks across NLP, CV, and vision and language domains, and it has actually impressive performance on all of them. This is a massive step compared to UNIT, where we only tested 8 data sets, 8 tasks and 9 data sets. And this is 35 tasks, which is very huge compared to what we were doing before. And data and models and everything is public for this particular model. So how does it look like? So think about all of the data that we have publicly available, which is unpaired text, all of the data sets such as file, common crawl, and everything which doesn't really have images attached to it. Then unpaired images such as ImageNet and all of the vision classification data sets. And then the image text pairs from PMD or Lion, for example. So we want something in middle, which can give you visual recognition, like tasks like ImageNet classification, the language understanding on Glue as well, and then multimodal reasoning, for example, VQA, Clever, and all those data sets in a single model. How do we achieve that? So FLAVA is a multi-domain joint pre-training architecture or like objective, where you can leverage the objectives from all of the unimodal domains and just learn them jointly. So in FLAVA paper, we show that how you can actually combine them together in a single architecture by extended unit and learn them together so that you can actually solve all of these tasks together by just fine tuning or even doing zero shot or doing linear copy. So how does it work in practice? To avoid mixing of responsibilities, so we have tested mixing the encoders together as well. It doesn't really work. So you want to separate image and text encoders because they learn very different kind of embedding. So you want to separate them. So to avoid mixing of responsibilities, separate image and text encoders are used in FLAVA. And for example, to train the image encoder, we use MIM loss where you mask the image. Like you basically in the VIT, vision and transformer, you convert the image into patches. You mask these patches and you try to recreate these patches again based on the extra information present inside the image. So the masking ratio is super high. So you are actually not seeing a lot of the image and then you try to reconstruct it. And then you have just like a vision task head on the top of the image encoder. So this task doesn't really see NLP or any other data that comes in. So the image task is only cares about the image data itself. Then you also add a text encoder head, and then you use any sort of NLP loss that you care about, a pre-training loss. In this case, it was MLM, mass language modeling. And then you take all of the unpaired input text and just pass it into the model and then train this task head on top of the text encoder. When you have like the tasks that care about both text and images, you will add an extra encoder on the top, which takes the output from text encoder and the image encoder and directly pass it inside the multi-modal encoder, which is maybe like 6 layers, the half of the layers of the text and image encoder. And then you apply all of the multi-modal pre-training objectives on the top of the multi-modal encoder. So like ITM image text matching, because we have captions, we try to match them with non-matching captions and the matching captions as well. And then you have global contrastive loss that doesn't really go to the multimodal encoder, but only works on image and text encoder, similar to the clip objective, where you try to like align image and text embeddings into like same semantic space. Then you also have like the masked multimodal modeling, where you actually mask both the image as well as the text, and you try to predict both of them through the other modality. So you mask either one, like the image, or either you mask the text and you try to predict it through the other modality, whichever is present. So this is how it works. So it's like a very big architecture with 5 losses on top. And you have to like basically sample the data sets accordingly so that you learn them properly. So how does it work in practice? It has actually very good performance compared to like visual BERT, clip on most of the image tasks, and even BERT on NLP tasks, and then also much better than unit, which was like just directly trained. So overall, like the global average of FLAVA is global macro average of the FLAVA on all of these tasks is much higher compared to any of the baselines. So for more details, you can just scan the QR and like see all of the tasks. There's a big table in the paper that you can see for all of these tasks. So the next key challenge that we usually see is that the current evaluation benchmarks are not relevant and saturated. So the problem is that once you create these models, they are already very good, that the already existing benchmarks like just saturate or like are very close to the human accuracy. So this chart is for the VQA V2 data set. And over time, like since it was introduced in 2015, the performance is almost saturated and it's almost close to the human performance. And the models are not achieving much. But the question is like, have we actually solved visual question answering as a task? So in the next few slides, I will show some data sets that I have with others like created over time to like actually test these various capabilities in the models that we care about, but the current benchmarks don't really test. So the first one is hateful memes, where you have an image and you have like a hateful text, which might be like not hateful in certain contexts, but might be hateful in some certain contexts. So the model has to tell whether this particular meme or like this image with text is hateful or not. So this is a very hard task. When it came out, like most of the models were doing at random. As of now, the best model with a lot of like hyperparameter tweaks and a lot of external knowledge is doing 78.4 ROC AUC, and FLAVA is doing 77.7. But the human accuracy is around 84. So there's still a way to go, but it does test like whether these models can understand hate speech or not. And then there is Winogrand, which is a very interesting data set. So you have the same text, same words in two separate images, but their word order is different. So when the word order changes, the meaning of the sentence changes. And we have like aligned images with these texts, and the model has to differentiate which caption belongs to which image. So there are like cross groups that you have to differentiate. So at this particular data set, like all of the current models are doing very bad because they don't really understand like how the context changes when the words shift. So the best as of now is 14.5, which is very low. Like I think the score for the random would be 13.3. And like this one is 14.5 and it's very low, and FLAVA is almost close to that. So most of the foundation models are not able to understand the true relation or the reasoning or the compositionality behind the sentences and the images. So human accuracy on this one is very high, and like it's almost close to like 90. And like most of these models are not anywhere close. And we talked about the VQ before, and as the graph shows, and as the models say that they have solved VQ as a task, and we were curious about this, whether it's actually solved. And so we collected data set on top, which is collected adversarially. And we saw that it's actually not anywhere close to solve. The human accuracy on this data set was 85, whereas the best model at that particular point of the time, which was SOTA VQ model, was only doing 34.3%, whereas FLAVA does 36.4. Finally, like there is a missing component in even in DALI like models, that they are not able to understand the text inside the images. For example, like just see the question, like what does it say near the star on the tail of the plane? These models are not able to understand the text written inside the images, and they just don't understand how it's done. Like DALI, if you ask it to generate certain sentences or with text in it, it just like basically creates a clutter on top of it. So we actually like created data sets for like captioning on these images and also like visual question answering on these images. And like FLAVA does really well on it as of now, 38.4, but like best without OCR is only 34. So there's much to do here, like in the terms of these things. So what did we learn today? Like for the key challenges, like let's revisit them. Jointly learning across domains, you can use unit. For cross-modal data, you can use PMD or Lion. For jointly pre-training, you can use FLAVA objective, and you can basically extend it to even audio by just adding a new audio encoder on top, and then it should work out of the box. You just need to tune the samplings of the data sets themselves. And then the current evaluation benchmarks are not relevant. So I've introduced a lot of the newer benchmarks that we worked on, which try to like focus on specific capabilities of the models. Finally, the future. So we are actually working on an extension of FLAVA, creating a bigger model for FLAVA, which we call FLAVA XL, by using Lion and like some of the other data sets that are not publicly available, like the Pile bigger version. Then also we are doing a Flamingo, which is like a chatbot just on top of images, reproduction and Hugging Face. So we will be seeing sooner more of these vision and language foundation models in open. And Unit is available to MMF, and FLAVA is in Hugging Face transformers. And thank you for listening to the talk.